Okay, so in the previous lecture I showed you how we deal with homogeneous, directly or strong boundary conditions, and you saw that the preferred approach was always that we do as if there was no boundary conditions when we assemble the linear system, or at least when we compute the local contributions, and then we deal with boundary values only in one particular place, namely either when we copy the local contributions into the global matrix or after we have assembled the global matrix. And that's the only place where we have to worry about boundary conditions, because then we end up with a linear system for which the solution is automatically correct for all of the boundary nodes. So the remaining question was what happens if you have inhomogeneous boundary conditions. So let's say something like u equals g on the boundary where g is not equal to 0. And that's what I would like to talk about in this lecture. That's sort of a follow-on on the previous one. So this is lecture 21.65. How do you deal with inhomogeneous boundary conditions? And like I said, it's directly conditions for the Laplace equation, but in reality I'm talking about inhomogeneous strong boundary conditions, and it doesn't actually really matter which equation we talk about. So to consider an example, let's think about the Laplace equation. So I'm going to consider minus Laplace u equals f. In the domain and on the boundary, I'm assuming u equals g. So for simplicity, now I'm going to assume that g can actually be exactly represented by finite element functions. So let's say that would mean that in the simplest case, g is just a piecewise linear function between any two nodes on the boundary. That's of course in reality not usually the case, but let me make this assumption, and if it's not true, then I'm going to just replace g by the interpolation of g, for example. So I'm going to replace g by a piecewise linear function that at every vertex on the boundary, or at every node of the boundary, has the correct value. Okay, so that is an immaterial consideration. I'm just going to make my life a little bit simpler. But let's say from a theory, that does not pose any difficulties. So the general idea how to deal with non-zero boundary conditions essentially works like this. I'm going to represent my solution here. I'm going to decompose this into two parts, namely a part u0 and a part that I'm going to call g tilde. And they satisfy the following conditions. So u0 will be so that it has zero boundary conditions, okay? And then if I take this u and I put this decomposition into the equation here, then I find that minus Laplace u0 equals f plus Laplace g tilde, okay, and u0 equals 0. And then the question remains, well, what do I do with this g tilde? Well, so if I want u0 plus g tilde to be u on the boundary, and u0 has zero boundary values, then I need that g tilde equals g on the boundary. And other than that, in principle, I can choose g tilde arbitrary. So we call this a continuation. I only know what the boundary values of g are, but whatever its values in the interior, they're arbitrary. I can continue that into the interior, from the boundary into the interior, in whichever way I want. Of course, what I choose here, how I choose this, makes a difference for what the corresponding solution u0 is, because g tilde appears here on the right-hand side. Okay. Now, in the discrete setting, what I would like to do is I would like to solve this sort of equation here discretely. And so one of the things that is particularly convenient to choose would be that the g tilde, my extension, my continuation from the boundary into the interior, I would like to choose this in my finite element space. And I would like to do this because then I can reconstruct the solution UH of the original problem by adding the discrete solution to this problem here with zero boundary values, okay, plus g tilde, which is also in VH. So I'm adding two objects that live both in the finite element space, and as a consequence, UH also lives in the finite element space. If I had chosen this g tilde any differently, so let's say a function that solves the homogeneous Laplace equation with boundary values, so we call this the harmonic extension, then, well, this is a finite element function, but this would not be, and as a consequence, my UH would not be a finite element function as well. So I would like to choose this g tilde to be a finite element function, and I add it to the solution of the homogeneous problem, and that gives me the original problem. So there is a particularly convenient choice for this g tilde that everybody who solves PDEs on finite element methods uses. Namely, I'm going to choose g tilde in the following way. So on the boundary, it has the correct values. Okay, so this is an example from step 4, where the exact solution is 4x to the 4, probably plus 4y to the 4 here. And then in the interior, for all interior nodes, I'm going to choose g tilde equals 0. Okay, it's one of the many choices that I can make. And you will see in a minute why this turns out to be such a convenient choice for this g tilde. Namely, when you assemble a linear system that corresponds to this, so I would like to have an AU equals F, of course, but I need to deal with boundary conditions. So this AU equals F that assumes that I don't have any boundary conditions. I split the solution U equals U0 plus G tilde. So U0 is going to be the nodal values of my solution U0 that has 0 boundary values, plus capital G tilde. Capital G tilde is the vector of nodal values of this function here, right, of the little g tilde. So then I'm going to take this decomposition, put it in here. So I get AU0 equals F minus A G tilde. And this is now a problem that requires me to solve something with 0 directly boundary conditions, or 0 strong boundary conditions, okay? Well, I've shown you in the last lecture how we actually deal with this. This turns out to be a pretty simple problem. We know how to do this by now, okay? And so after I've solved this problem here, then I have my U0, and I get back the U that I really wanted, the solution of the Laplace equation with non-zero boundary conditions, by just adding the solution that I just computed plus the g tilde that I chose this particular way, and that gives me my U. So programmatically, what I do is I assemble my linear system as if there were no boundary conditions at all. Okay, I'm computing a right-hand side h that is f minus a g tilde. So a, that's the Laplace operator applied to g tilde. That's the Laplace operator without boundary conditions. Okay, then I have to apply the boundary conditions, the modifications to the linear system AU0 equals h. So I'm going to get a different matrix A and the different vector h out of this after striking rows and columns. Okay, I solve the modified system, and then I'm going to compute my U from the two components. And you will see that in reality, the steps 2, 3, and 5, they all can be done at the same time. So I'm going to just assemble as if I had no boundary conditions at all, just like I wanted it to, just like I explained what we want from a useful algorithm. So I'm going to assemble as if there were no boundary conditions at all, and then I'm going to do all of these steps here at once. So they give me a linear system that, if I solve it, automatically gives me the correct solution U here. So I can do it all in one step. To understand why that is so, let us look at how this vector g tilde, for example, looks like. Okay, so I chose this g tilde in a way that it has the correct values for all boundary nodes, and it is 0 in the interior. Okay, so g tilde is 0 for element 1, 5, and 6. So this is this and these two elements here. And for all of the nodes that's sitting on the boundary, it has the correct boundary values. So there would be g of x0. So g is the function that I have, so the boundary values that I want to impose, and x0 is the location of node 0. Okay, so that's the x and y components of the position of this node here. And the same thing for the others. You remember that if I go to finer and finer meshes, the number of interior nodes grows much faster than the number of nodes on the boundary. So in reality, this vector g tilde will be a vector that has almost all zeros. And that's going to be important for the steps that we're going to do next. So remember that g tilde is a very sparse vector. There's not very much in it. Okay, so what I need to do as part of the algorithm, you remember that I needed to compute a times g tilde. Okay, Now A was this 10 by 10 matrix that I have computed as if there were no boundary values at all. And now I need to multiply it with this vector g tilde here. And g tilde consisted of g of x0, g of x2 for every one of these boundary nodes. And if you look at this closely, what you will see is that, of course, well, because this vector here on finite enough measures has almost all zeros, what it really is, it's certain sets of columns. So let's say this column here times g of x0 plus this column here times g of x2, okay, plus column number 3 of the matrix A times g of x3. So I've written this over here on the right-hand side, okay. You also remember that the columns that I've isolated here, so the column 0, column 2, column 9, for example, these are all exactly those columns that I will zero out in this matrix in the next step, okay. So it's not just any set of columns, but it's exactly those columns that I want to zero out. So the algorithm that deals with this whole thing then works essentially like this. So I'm going to go over all of the boundary nodes, okay, so for I in the set of boundary nodes, I'm going to subtract g of xi times the ith column of A from the right-hand side. And I need to do this so I get a sum here, but you remember that what I really need to compute is f minus A times g tilde, okay? So it is f minus the sum of certain columns of A times the corresponding elements of g tilde, okay? So if I loop over this, I start with f, and then I'm going to subtract one column times the corresponding element of g tilde at a time, okay? So the algorithm is subtract g of xi times the ith column of A, and then I'm going to zero out the column and the row of A, and I'm going to set the diagonal element to 1, or like I explained before, to some other value, okay? And I'm going to set the ith entry of the right-hand side to g of xi, and you will see why I do this here, okay? What this algorithm does is it automatically yields the correct linear system, not just for the interior nodes, but also for all of the boundary nodes. So the solution of the linear system that I get out of this automatically satisfies the boundary conditions. So I don't actually, after solving the linear system, have to compute u equals u0 plus g tilde. I automatically get it as part of the process. So to show you how this works, right, so I have assembled my linear system as if there were no boundary values. It's a 10 by 10 matrix, okay. Then the first step was that I subtract, so I loop over all of the boundary nodes. These are 0, 2, 3, 4, 7, 8, 9, okay. So I start with I equals 0 with this one here, okay. So I subtract the multiple of this row here times g of x0 from the right-hand side, okay. So I get this thing here. And then I zero out the column I, so in this case the zeros column, and in practice, of course, I do this at the same time. So I read A0, 0, I subtract this element from the right-hand side and immediately set it to 0. And then I read A1, 0, I subtract it from the right-hand side and immediately set it to 0. So I only need to touch the matrix entries once. Then I'm going to zero out the corresponding row and the element on the right-hand side, okay. Then I'm going to set a 1 to the diagonal, and I'm going to set the right-hand side to g of x0, okay. And you see already this yields 1 times u0 equals g of x0. So that automatically means that the solution of my linear system is going to satisfy the correct boundary values for node number 0, okay. Very convenient property. And then I'm going to do the same for the next degree of freedom. So the next degree of freedom on the boundary is 2, okay. So I'm going to take this row, or whatever is left of it, and I'm going to subtract this column times g of x2 from the right-hand side, okay. I'm going to zero out the entire column. I'm going to zero out the entire row. I'm going to put a 1 on the diagonal, and I'm going to replace the right-hand side by g of x2. And lo and behold, I get the correct boundary values for u2 as well, okay. And I repeat this for boundary degrees of freedom 3, 4, 7, 8, and 9. And in the end, I end up with a linear system that looks like this. No, it's too fast. So I get a linear system like this, where again I have certain ones on a diagonal for every boundary degree of freedom. But now I don't have zeros in the corresponding places here, but I have the boundary values that I want for these degrees of freedom. Okay, and then for the remainder, for the 3 by 3 linear system that really determines all of the interior degrees of freedom, I have not just f1, f5, and f6, but I also have the corresponding elements that result from subtracting 8 times g tilde. Okay, so that was the algorithm by which I construct this. So I get a linear system that automatically satisfies the correct interior values and the correct boundary values. So to sum this up, conceptually, what that means is we can decompose the solution into a part that is 0 on the boundary and a part that satisfies the boundary values, and then we use essentially the algorithm from the previous lecture with just a small modification. And we can do this both at the global level, so we can first assemble the linear system and then eliminate boundary values by zeroing out rows and columns. And there's a very similar algorithm that would do the same kind of steps during the copy local to global method. So during the time when we copy or add the local contributions into the global matrix, we can also do these sort of modifications that take care of the corresponding elements that go into the right-hand side. So these things here can also be computed at a time when we do the copy local to global operation. So to show you again how this looks like for these approaches 2a and 2b in the current version of step 4 and step 6. So in step 4, basically it's exactly the same as before. The only difference is that we call interpolate boundary values with a function object here that describes the non-zero boundary values. Before we just had a function, let's say 0 function that describes 0 boundary values. And I'm going to get a map from the boundary degrees of freedom, so 0 to, what was it, 7, 8, 9, for example, to the corresponding values g of xi, okay? And then this function apply boundary values is also quite happy to take non-zero boundary values, okay? And similarly, I can do this in the approach that we currently use in step 6. So again, I call vector tool interpolate boundary values. I put the results into a constraint matrix, and again, I have to use whatever boundary object I have here. And then the distribute local to global operation takes care of this when we copy local to global elements. So I hope you understood that, well, there's a little bit of algorithmic trickery behind how we deal with strong boundary conditions, but basically there's no real magic there. It's just something that, let's say, somebody has to implement, but if we do it the right way, then there's really only one place where we have to take care of this. This is either during the local copy to global operation, or during or after the assembly where we have the linear system where we have to modify it. And the beauty of the approach is that all of the other places in your code don't really need to worry about whether a node is on the boundary or is not on the boundary. All that matters for all of the other places is let's say assembling the bilinear form, these sort of things. So in the end, it comes down to just an algebraic manipulation, right? Do I need to manipulate the local system before I copy it into the global system, or do I just assemble the global system and then I do some algebraic manipulation? But the algebraic manipulation at that time does not depend on the PDE that we solve anymore. So if you go back through the slides, you will find that I have not made any reference at all whether I solve the Laplace equation. All I have is a linear system AU equals F, and I want certain U's to satisfy certain values. Where that A came from does not matter. So the algorithm really works on an exclusively algebraic level with the matrix that comes from wherever. That's basically the way we operate with these sort of things. So that's what I had to say about how we deal with strong boundary conditions, and I think by now then you should have seen how, let's say, most of the important boundary conditions can be dealt with in practice. And I think with that, for now, I'll leave the topic of boundary conditions.